Good afternoon, everybody. It's a pleasure to, can you hear me? It's a pleasure to introduce today's speaker, a very good friend, colleague, and mentor of mine, Professor Nader Engheta. Professor Engheta is a full professor at University of Pennsylvania, where he holds the endowed professorship, professor chair, Neville Ramsey Professorship. He finished his bachelor's degree at University of Tehran, and then he joined California Institute of Technology, where he completed his master's degree and PhD degree with Professor Pappas. While he was a PhD student, actually, he also closely interacted with Richard Feynman and Max Delbrück during his studies, which are both Nobel laureates in physics and biology, respectively. Professor Engheta his primary appointment at the University of Pennsylvania is in electrical and systems engineering. He holds secondary appointments in the physics department, material science, physics and astronomy, and probably a few other departments as well. He has a wide area research interests, ranging from nanophotonics. His work on metamaterials is very well known. He's one of the first ones to start working in this area. One of the areas that I worked as a PhD student was on bio-inspired vision, which is a long interest. A lot of people know Professor Engheta from the electromagnetics antenna community as well as the metasurfaces community, but he did a lot of really interesting work on animal vision and polarization vision and multispectral vision as well. He's received numerous awards, and it would be too long to mention all of them. I would just point out a couple of them. A couple of days ago, he received the 2018 Pioneer Award in nanotechnology from the IEEE Nanotechnology Council. He received the gold medal from the SPI Society, as well as the gold medal from the URSA Society in 2014. And he's also a recipient of the IEEE Third Millennium Medal. He's a fellow of several international scientific organizations, of 7 scientific organizations: IEEE, OSA, APS, MRS, SPIE, URSA, and the AAAS Society as well. It's a great pleasure to have you here, Professor Engheta.
Thank you.
I have a little present from you from University of Illinois.
Thank you very much. I appreciate that. Thank you.
Look forward to your talk.
Thank you. Thank you very much, Victor, for the very kind and generous introduction. It's a pleasure and honor for me to be here. This is, I think, the 3rd time I've been at the University of Illinois, and it's a great pleasure to come back again, thanks to Victor, that provide me with the chance to come over here and see many of my friends, in the faculty. And so today, I'd like to talk about, as you see from the title of my talk, about some of the ongoing work that going on in my group under the title of extreme photonics. And I'm going to tell you what I mean by extreme photonics. But in order to have actually very unusual light-matter interaction, we need unusual platform, an extreme platform. And that's why we're going to talk about the connection between the concept of metamaterial and metasurfaces, and how we can use that in order to control and structure waves to do interesting things for us. Now, in my group, we are interested in this extreme light-matter interaction, and we are looking at these various different scenarios. Now, in the interest of time, I can't talk about all of them. But what I'm going to do, I'm going to show you 7 slides, each of which talks about one of these, extreme scenarios. And after that, I'm going to concentrate on 2 of them for the rest of my talk. And I'll be available after the talk if anybody interested in other 5 topics as well. But first, I'd like to tell you about some of the background, just a few slides on the history and background of metamaterials. Now, we are all familiar that light-matter interaction is governed by the laws of electrodynamics, both classical electrodynamics, Maxwell's equation, and all the good things about it, and also quantum electrodynamics and quantum photonics. And of course, usually when we deal with this type of problem, as you're all familiar with, we are dealing with parametrization. So we like to deal with the parameters that involve in this type of interaction, that you're all familiar with that. permittivity, permeability, conductivity, nonlinear susceptibility, chirality, and so on and so forth. Now, the materials that nature has provided us, and some of the derivatives of the material of natures that we are familiar from periodic structures and all the other materials that combine by this, have some range of values for these parameters that we use them. However, the concept of metamaterial would help us to actually engineer materials whose parameters would have values outside this region, obviously physically realizable. And the concept of metamaterial actually is quite straightforward. So what you need to do is to start with the host medium, and then you embed them with man-made elements, which we call it inclusions. And with the proper design and proper material composition of that, when you have electromagnetic waves going through this, it's going to excite or induce electric and or magnetic dipole moments on each one of these. In turn, those things re-radiate. And for the observer sitting outside of this structure, they would look at this and they would see an effective permittivity of this, an effective or homogenized permeability and index of refraction. So you can actually engineer the index of refraction and the permittivity that you like to have, which could be quite different from the permittivity and index of refraction of each of these constituent elements. And one of the reasons that metamaterial has become very interesting and powerful is the fact that you can control many of these elements. You can control the composition of this element, alignment of that, arrangement of this, density of them, host medium, and last but not least, the geometry and shape of this inclusion. And particularly this last item is important because with the advent of nanoscience and nanotechnology, you have much more ability to actually control the shape of these structures. And over the past 2 decades, there have been many, many examples of various different types of metamaterials. Here I'm showing, some samples of various different groups that made metamaterial, but by no means this is an exhaustive list. I can show you, many, many pages on various different types of metamaterial. The fact that you can actually control and design the permittivity and permeability or any other material parameters of this structure will give you an interesting ability to actually do interesting applications. And over the past several years, various different applications have been studied by the metamaterial community. Cloaking, super lens and hyper lens, ultra thin cavities, transformation optics, electrically small antennas, epsilon near zero and mu near zero structures, some of which I'm going to talk about today. The concept of optical metatronics or optical nanocircuitry, and metasurfaces, which would be a 2-dimensional version of metamaterial. And again, this list can continue as well. But then one of the interesting questions to ask is, what's going to happen in the future? But these are some of the applications that have been studied by now. So looking to the future, of course, nobody can really predict. Nobody has, a crystal ball to say what's going to happen in any field. But we can have some interesting suggestion and vision for that. And in my group, by the way, we are actually working to take these concepts to the extreme scenarios. And I mentioned I'm going to tell you about the 7 different extreme scenarios we have in mind. So under the type of extreme photonics, the scenario number 1, which we have recently developed, is a concept that we call it photonic doping. And it would be the photonic analog of electronic doping that I'm going to talk about a little bit later in my talk. And this has quite a series of interesting useful and unusual features, one of which is this concept over here that would actually allow us to have something that I call it a single inclusion metamaterials. In other words, usually the concept of metamaterial is by including an array of elements, you can control the effective permittivity. But we are showing that under certain conditions, which I'm going to mention later on in my talk, even one inclusion into a material can change the property of scattering significantly. And you will see how that happens. The scenario number 2 is basically what should we do if we have this type of material to actually control the thermal emissions. Now, I don't have time to go through this, and I just show you this slide. If you're interested, I can talk to you after the talk. But we have shown that if you have a material whose permittivity is near 0, and you do this photonic doping on that, you can make the thermal emission to be spatially coherent. Now, usually thermal emission is incoherent. But with this type of material, you can actually make the thermal emission spatially coherent. So as a result, this structure can actually emit the thermal emission just like an antenna arrays that would do in a particular directions. So you can have a directive thermal radiation. And this can be done based on the materials. Scenario number 3 is a very special type of cavity that we introduced recently. Often when we talk about cavities, we know that the resonant frequency of the cavity can change if you change the shape of the cavity, naturally. But with this type of materials, we can show that there's an interesting class of cavities that are geometry independent. In other words, you can change the external shape of the cavity without changing its resonant frequency. And as a result, we actually find out quite an interesting scenario, which is the equivalent of bound state in the continuum in photonic system. Now, many of you are familiar with electronic bound state in the continuum, but here we show that you can actually have an open cavity system that you can actually hold electromagnetic energy in an open cavity. And that system would be a photonic equivalent of bound state in the continuum. The extreme scenario number 4 is how to actually, when we were studying this type of cavity, we said, it's very interesting, because in the field of quantum optics, you always deal with interaction of excited atom with a cavity. So what if I have a cavity in which the resonant frequency is independent of external shape? What kind of quantum optics we have? What kind of quantum electrodynamics we have? So we decided to actually build an interesting version of quantum electrodynamics based on this type of cavity. And as a result, we could show that you can actually have a very interesting way to engineer the Rabi vacuum frequency, this should be 1I, without detuning the cavity. Now, generally, in any quantum optical system that you work with a cavity, if you change the shape of the cavity, the resonant frequency of the cavity will change, and the system would be detuned, but not in this type of cavity. You can change it, and the resonant frequency would stay there. Scenario number 5 would go back to some of the work we did earlier in 2005, which what we did, we said, in electronic, we have the concept of lumped circuit elements. All of you in electrical and computer engineering are very familiar. The first course you take in circuit, they tell you we have resistor, capacitor, inductor. The question we pose is that, why is it not the case in optics? Can we have the nanostructure in which, when you illuminate light to it, it will behave as optical capacitor, as optical inductor, and optical resistor? And indeed, we showed that that's the case. And now what we are doing is that we are actually looking at the quantum optical aspect of that. If we have these nanoparticles that behave as optical lump nanocircuits, what kind of interesting quantum system they behave? So now we are able to actually modularize the Hamiltonian of a quantum optical system, just like what the circuit designer would do with the circuit elements. Very similar, actually, analogy exists between them, and a lot of the formulation of the circuit design can come into the quantum optics of this. Metasurfaces, of course, is another passion of ours in my group. And what we like to do is to design interesting metasurfaces that would have application in quantum optics as one area of application. And one of the problems that we are studying is the following, that is it possible that I can design a metasurface such that when I send a wave to this metasurface, entirely transfers through that, in other words, with transmission near 1. However, the field distribution near this metasurface is anything you like to have. So in other words, you would have a very interesting patterning of the field you like to have, even though the wave actually penetrates through. So if with that, you can have a cascading system over here, that the light is going through this, and then each one of them would have a different field distribution near that, which in that case, you can put a quantum emitter near these surfaces, and then the Purcell effect of each one of these can be designed independently. So this is one of the simulation results that we have over here. You notice that this one, we design it such that the wave is coming through here, goes through a very narrow aperture, and goes through with no reflection. So there's no reflection. Its transmission is 1. And finally, the extreme scenario number 7 is that we say, OK, can we actually design a material Now, in the previous slide, I showed you that we can do optical structures that will work as a circuit. In other words, material becomes circuit. But now, what we'd like to do is that can material be put together such that when you have a wave going through this, it will actually do analog computing for you. In other words, it can actually perform mathematical operations. So about 3-4 years ago, we proposed this idea that we call it informatic metastructures. In other words, can we actually design a material that would do mathematics for you, that would take the derivative for you, that would take the integral for you as the wave goes through it. But now we are actually changing our goal to a wider and more general goal. And the goal that we have right now is that can we design a metamaterial and material structure that would be able to solve the integral equations for you. As the wave goes through it, can we actually solve the integral equation for you? So these are the 7 scenarios I'd like to tell you. But now for the rest of my talk, I'm going to concentrate on 2 of these, maybe even 3 if time permits. But I'm going to start with the last one first. So in other words, could we actually design a platform such that as you send the wave through this, you would be able to solve mathematical equations? And as a result, as an example, we decided to actually solve a very general class of Fredholm integral equation of the second kind, which is the most general linear integral equation you can have. In other words, what we are trying to do is that let the materials do the math. In other words, we design a material, we send the wave through it, and the mathematics would be the outcome of the wave that's come out of it. So let's do it. So first, let's start as a background over here. So the original question we ask is the following. Would it be possible that I put a collection of nanostructures next to each other such that with the proper shape of this structure, with the proper material of this structure, and the proper location next to each other, such that when you actually send a wave to this, obviously it's going to scatter, but what comes out of the other side will be, of course, a different function. Now, these are monochromatic waves. Let's say we're not changing the frequency, but I'm talking about the spatial distribution. Now, would it be possible a priori to design this structure such that it will give you that specific transfer function you have in mind? Now, that's something the circuit designers do all the time, by the way. But now we would like to do it in nanophotonics. We would like to do it with nanostructures. So this was our goal. And as a first step to this, as I mentioned, 4 years ago, we proposed 2 approaches to do that. One is to use, graded index structure that would do the Fourier transform in the space domain, and then design a metasurface over here that would do mathematical operation for you. And another approach we did is that to have actually layered structure such that you engineer the Green's function you like to have. Now, the regular medium has its own Green's function when we want to solve, Helmholtz equation. What we said, we would like to actually put the materials together to actually give you the Green's function you like to have, not what the nature has given us. And indeed, in this example, you see that we design a layered structure such that it will take the second derivative, special derivative for you. Now, why second derivative? Because second derivative is the edge detector in image processing system. In other words, with this structure, you can have the edge detection of your image entirely in analog system. You don't need to actually do the raster scan of your pixel and then find the differences between them. This will do it in one shot, actually, entirely in the parallel system as the wave goes through this. But this was what we did about 4 years ago. But now we change our paradigm, as I mentioned. What we like to do now is to solve this general integral equation. Now, this is very general. The kernel is given to us. Remember, depending on the problem of interest, you know the kernel. The input function is arbitrary. You can put any input function you like. And as a result, you would like to find G. Now, of course, this is a very well-known, Fredholm integral equation of second kind, completely general there. But before I show you how we do it, I'd like to emphasize one point, actually 2 points. One, this kernel is intentionally not y minus y prime. In other words, it's not translationally invariant. That's important because if it's translational invariant, I can do the Fourier transform and I do simple approach. Intentionally, I don't want this to be k of y minus y prime. So I cannot do Fourier transform. That's one thing. Second thing, this limit from a to b, completely arbitrary. It's not from minus infinity to plus infinity that I can do convolution. It's not. So this is not a convolution aspect. This is very important, and we're going to keep it general that way. So how do we do this? First of all, if I have a design material, as I showed you in the previous slide, I can design a material such that if I have an input gy, I can get the output to be this. Now, that's doing the mathematical operation that we did about 4 years ago. But in this case, g is arbitrary. But of course, in the integral equation, g is not arbitrary when you give u. So this by itself is not going to do the work we want. We have to do something different to this in order to be able to solve the integral equation. What we need to do is to have a feedback. So if we create a feedback over here, then this system would have an eigensolution that would be solution to this integral equation with an input. Now, this system doesn't have an input yet, but I have to put an input over there. So one of the geometry that we are looking at, and you're going to see, by the way, how we did it, is that we are looking in the waveguide system with the very special type of metamaterial that we designed over here in order to do this kernel over there. So let's go through this to see how we can do it. So first, we have to design the optical kernel to do this operation. So if I start with an unknown epsilon x and y, and I have an incident wave coming like this, I have to choose this epsilon x and y such that the output becomes this operator. And there are different techniques to do that, which I will tell you in a second. But of course, this by itself is not enough. I have to bring this wave outside and bring it back over here. In order to do that, we decided to actually go to the waveguide system. Rather than open space or free space optics, we decided to actually have n waveguides coming in and n waveguides going out. And in this way, we can actually have the feedback system better because I can bring these waveguides back over here. In other words, we are envisioning something like this. Now, if you notice over here, this is like, n-ring resonator, if you will. Now, intentionally, of course, the length of this waveguide should be such that the phase and magnitude here should be the phase and magnitude there, obviously. But that's easy to do. But it's interesting that this n-ring resonator, they're not just a simple n-ring resonators. They're actually coupled through this block of material over here that gives us that kernel. So this is very interesting. In other words, this becomes one unit, a hybrid ring resonator whose eigensolutions can be solution to these integral equations. Except I have to feed the light into the system. So far, it's just a closed system. So what I need to do, I need to have a coupler bring the light inside or a wave inside, and I need to have a coupler to read the output coming out. So something like this system we design. And now let me show you a couple of simulation examples over here. First of all, we said, OK, let's try to see whether we are right. But before you give me the kernel and I decide what is the epsilon x and y, let's start with an epsilon x and y to see what kernel do we get. So we started with some arbitrary distribution of scatterer inside this box, 3 by 3. And it's very easy to find the kernel of this. So we excite every port separately, and we look at what comes out of this. And this is a coherent system. In other words, we look at the complex number there. You do, and then excite the second one and see what comes out over here. You excite the third port, it comes out over here. And then this would be the kernel that you have there. Now, there's nothing magic about this kernel because we started with an arbitrary distribution. The important thing is that to do the reverse of that. In other words, you give me this matrix, and I tell you what materials do we have there. But before we do that, we wanted to see whether this system would solve the integral equation if I use this as the kernel of that integral equation. So we said, OK, let's come over here. Let's put a feedback over here, kind of like this. And let's try it. Let's try for simulation. So imagine I put the input being waveguide 1 is launched and excited, and the waveguide 2 and 3, no excitement there. And then we'll look at what happens with the final solution over here. So see what happens. These are my input coming in. 1, 0, 0 is coming in, feeding into this, 3-ring coupled resonator over here with the special kernel that you see over there. It goes over here. It establishes with the final steady state solution that we have there. Now, let's come over here and find the 3 complex numbers over here. that would be solution to our integral equations. Naturally, it comes out just by this interaction. So how do we prove that? OK, so let's do this. One, we're going to look at the result of this simulation that we have. And in order to see whether this is indeed the result of the solution to that integral equation, we have to use an independent approach to that. And let's say we use the exact result coming from mathematical. OK, that's the exact solution. And let's compare them. And this is the comparison. So real part and imaginary part. Solid line is the result of this device, simulation of this device. And the dashed one is an exact solution. So we see the agreement was good. So we were encouraged that that would work. This is for the case that we excited with the port here, but the other two, 0. So then we said, OK, what would happen if I excite this one? Obviously, the distribution is different. So because the input to the problem has changed, so obviously, when I come over here and I read this one, I get the different solution. And that makes sense, because my integral equation should have a different solution if I have different input. And you notice, again, the agreement is very good, both real and imaginary part. And if we excite the third port, the same thing. We can get a good agreement. But this is for the forward problem. That was just, to warm up. What we needed to do is you give me the kernel of the integral equation, and I go and find out what is that epsilon x and y. So we decided to do that. So let's assume we start with this kernel. Now, we have studied several kernels, very, very general. For the interest of time, I'm just going to show you one result over here. So we decided to look at this kernel, and you notice that this is not y minus y prime. So how do we go and do this one? There are interesting, well-known technique in optimization. There are several different optimization techniques, but we decided to use the optimization technique known as objective first optimization technique that pioneered by Yelena Vukovic at Stanford, David Miller, and Xianghui Fan. And one of the things we decided to do is that if you look at that optimization and apply this kernel, what do we get over here? By the way, we also have used another approach of the Mach-Zehnder interferometer to create this type of kernel, but for the interest of time, I don't have time to talk about this approach. So let me choose about the first approach. So in this optimization technique, we start with a blank slate. We go through this optimization to try to find what is the permittivity distribution that will give us that kernel. It becomes this. Now, this is interesting. This is the distribution of a permittivity between 1 and 2 that if you excite from this end and look at the output, you're going to get that kernel. And we're going to show that that's the case. But we were not happy with this because this distribution is gradual. It's grayscale. Now, I may not have a material that has exactly 1.3 permittivity. So it would be better to actually make this a binary system. And we did it. And that becomes that. So what you see over here, the black one is epsilon 2. By the way, there was nothing magic about epsilon 2. We just chose that number, arbitrarily. And the gray one over here is air. So if I get a dielectric material with epsilon 2, and I make these holes into them, this structure was going to give us this kernel. Let's see whether it does or not. So this is a field distribution that you will see over here when you excite it from this port. And this is the distribution of permittivity that you have there. Just to give you an idea, this is about few wavelengths. This is about 10 wavelengths over here. But now there is no feedback there yet. But we have to put the feedback. But before I show you this, let me just excite every one of these in our simulations. And for every one of them, we're going to see what happens to the output of that and to see whether that would give us that kernel. Now, we want to have that kernel. So ideally, we would like to have some kernel which is like this in a scattering matrix. Ideally, we would like to have the kernel be like this. Reflection, we would like to be 0. By reciprocity, this one should be conjugate, the conjugate Hermitian of this. And this one is when you excite it from the other end. But we don't need that. Now, this is the ideal S matrix we want to have. What happens in this one is this. So it's very close to ideal. There's some little reflection that we have over here. But even the presence of that reflection is not going to affect our result that much. So the system is robust. But now I have to put the feedback over here. So let's do it. So when I put the feedback over here, and I use this as my input, arbitrary input, there's nothing magic about this, but we'll put it 0, 0, 1, 0, 0. So 0, 0, 1, 0, 0 is going to excite this entire system. And when I come over here and I read off of these 5 points over here, I get the solution to our integral equations. And that answer is this. So the solid line is the result that comes from this structure and this simulation, and the dashed one is the exact solution that we should have from this integral equation. Now, we decide to have different input. For example, we just change the input like this, 0, -1, 1, 1, 0. So it could be any number you would like to put it input there, and look at the distribution, and you get this input there. Now, right now, we have designed these things completely, and this is the structure that's being built as we speak, by the way. I mean, this structure, we build it, we actually take into account every single aspect of this design. You notice we have 5 waveguides feeding over here, and the 5 other waveguides get the result out. This is the structure we have with Roxolate. And actually, this is being built. It's going to be ready in about 3 weeks, 4 weeks. And in 3, 4 weeks, we're going to do the experiment on this in microwave first. We are very excited about this. If the result of this microwave experiment turns out to be what we predicted through our simulations, then we're going to go to the nanoscale. We're going to take this into the silicon, and we're going to try to actually do structure in the near IR, like 1.5, micron. And that would be quite exciting because we can combine it with silicon photonics. So stay tuned. In about 3, 4 weeks, we're going to get this structure and start doing the experiment on that. But based on the simulation that we have done on this actual design, it should work. But of course, we wait until we actually do the experiment to see what happens. So let me change the gear. The second scenario I promised to talk to is photonic doping. Very different subject. So we are all familiar with electronic doping. We are in electrical engineering department, so everybody knows what is the electronic doping. Electronic doping is that we start with a pure intrinsic semiconductor when we teach to our undergraduates. It has certain electronic property, but what we do, we come and of course put the doped semiconductor as an donor and acceptor there, and of course that changes the electronic property. We all know that. But we ask ourselves this question, is there a photonic version of that? In other words, what if we start with a pure photonic materials, and I'm going to tell you what I mean by that. And of course, this has certain scattering properties, certain photonic properties. But what if I come over here and I put a photonic dopant there? What do I mean by photonic dopant? Let me assume I put a dielectric particle there. Just a simple dielectric particle. Now, I ask the question, would this change the scattering properties of this? The answer is obviously yes. But would it change significantly, even if it is 1? Now, in order to answer that, we said, OK, what kind of pure photonic material we should start with? Now, this concept, by the way, with regard to the pure photonic material, in the past, people have looked at the photonic bandgap structures. So they started with the photonic bandgap structure at the bandgap, so no light will go through. If you go there and remove one of the elements, you create a defect. We all know that creates local density of state, and the wave can go through that with a particular frequency. But we didn't want to do the photonic bandgap structure. We want to do another interesting material. And that is, what if I start with a host material that is ENZ? And ENZ stands for epsilon near 0 materials that we have developed in my group. And I'm going to tell you what that is. So you will see something quite interesting, that if I start with epsilon near 0 material, and I put 1 dielectric rod there, I can change the scattering structure significantly, and you will see how. But what is epsilon near 0 material? OK. So let's go back to our friend Maxwell's equation, time harmonic Maxwell's equations. And when they teach us Maxwell's equation, by the way, in the first course in electromagnetics, they say this, that if I have a DC scenario, which means omega equal to 0, then I have electricity and magnetism will be decoupled. That's the first thing they teach us. But we try to ask another question in the context of metamaterial, is it possible to come up with the structures or material platform such that electricity and magnetism would still be decoupled, but the field will be dynamic? In other words, the frequency would not be 0. Is it possible to do that? The answer is right in front of us. If I can create a material or material structure such that epsilon would be 0 and mu would be 0 at the frequency of operations, then I get, again, electricity and magnetism decoupled. But this is very different because the field is not DC. is changing with frequency omega. And from the outside observer, electricity and magnetism would look like being decoupled. Now, if that is the case, that means from spatial distribution point of view, it looks like a static distribution, but it's not static at all. It's actually changing with frequency omega. And you're going to see actually the implication of that. So in other words, the index of refraction would be near 0. And that actually opens up quite a series of interesting phenomena, which we call it under the near 0 index optics or low index photonics. So in the interest of time, for the rest of my talk, I'm going to actually tell you some of these features of that would happen. Now, before I go any further, let me just make something extremely clear, because sometimes there's this confusion. When I say index of refraction near 0, immediately comes to your mind that, OK, phase velocity should be infinite. Is that possible? Is not violating, special theory of relativity? No. We know that the energy velocity should be less than velocity of light. Phase velocity could be any number we want. In fact, in a regular microwave waveguide, when you operate near the cutoff, phase velocity is very, very high. In other words, wavelength would stretch. So another important point is this system is dispersive. In other words, the group velocity and energy velocity certainly is less than velocity of light. So when I say that the index of refraction is near 0, I mean for the steady state signal. In other words, in the transient part, of course, everything is big mess. But then after it establishes with the steady state, then the index of refraction would be near 0, and the wavelength would be stretched very long. And with that in mind, so we're going to see what happens. Now, so let me take you back in the history. Almost 12 years ago, in my group, we started to look at this ENZ property, and we actually came up with a very interesting feature of this epsilon near 0 material. This paper published in 2006, and my good friend and collaborator, Mario Silveirinho, now he's a professor at the University of Lisbon in Portugal. So what we did, we actually started with a very simple question. And the question was this one. What if I start with a parallel plate waveguide? So let me assume I have a very simple parallel plate waveguide. Perfect conducting plates. Over here, I have a simple TEM mode propagating down this waveguide, the simplest possible mode. And imagine I have another waveguide, again, parallel plate waveguide with a perfect conducting wall, and this is also another TEM mode. OK, very, very simple geometry. Now, what I'm going to ask ourselves is this. What if I connect these two waveguides with this region that is completely arbitrarily shaped? Completely arbitrary shape. Now, what would happen, do you think, to the wave that's coming from here? I mean, you would say, OK, it's going to reflect part of it. Because, of course, this throat of this waveguide is narrow. It's going to reflect. And yes, that would be the case. But we ask ourselves this question. What if I come over here and I fill this region with a material with permittivity near 0? Do I get something unusual there? Now, why did I think that way, by the way? I mean, was there a reason that we were actually even asking that question? Yes, there was some intuition in my head. And that is, if the permittivity is near 0, the index of refraction here would be near 0. And index of refraction would be near 0. That means wavelength would be very, very long for the frequency of operation, which means the phase should be uniform there. So it means the phase of here and here should be the same. So if the phase is here the same as this one, this will radiate in this structure. By conservation of energy, reflection should be less. So it would be interesting. Do I have very unusual, tunneling? That was our thought at that time. But at the same time, there was another intuition against that in our head. And that is this. When I have permittivity near 0, the wave impedance inside this material is infinite. Square root of mu over epsilon. It's very high. And the square root of mu over epsilon over here is just, 120 pi. I mean, standard wave. So do I have a huge impedance mismatch over here? And the whole wave would be reflected? Yes, you might say, I have a phase equal to 0, the same there. But if the magnitude is 0, it's useless. So we decided to actually see whether we can solve this problem. So Mario Silveirinho was visiting my group for his sabbatical. And I said, Mario, if you're interested, we can work on this together. He said, yes, let's do it. And we got lucky. We got lucky because we were able to solve this problem exactly analytically. I mean, with an exact solution to this. The only assumption we are making over here is this system is a two-dimensional extended over here, and the boundary is a perfect conductor, and this mode is TEM. That's the only assumption we are making. And with that, we were able to come out with this expression for the reflection coefficient of the mode. Now, if I want this reflection coefficient to be 0, I need to make sure the numerator is 0. But the numerator has a real part and imaginary part. So I have to make sure both of them would be 0. So let's do it. So I want to make sure A1 minus A2 is 0. But what is A1 and A2? Is the height of this waveguide and height of that waveguide. OK, so the two heights should be the same, input and output. Not a big deal. The third thing is that this imaginary part should be 0. But this imaginary part is a combination, a multiplication of 3 parameters. Any one of them I make 0, I achieve my goal. Either I have to make k naught equal to 0, but what is k naught? It's omega over c, velocity of light. So it means if I make omega equal to 0, then I get 0. But that's not interesting. Omega equal to 0 is a battery. So if I put the battery over here, I get the same voltage there. OK, not a big deal. Or I have to make mu sub r equal to 0, which means in addition to permittivity being 0, I have to make its permeability 0 too. 12 years ago, we didn't want to touch that. Now we are doing that. But at that time, we didn't want to touch mu. So I said, OK, that is not good either. So how about this guy, A sub d? But I haven't told you what A sub d is yet. A sub d is this cross-sectional area. In other words, if I make this cross-sectional area smaller and smaller and smaller, the reflection coefficient becomes less and less. Very counterintuitive. In other words, if I get the throat of this waveguide and I make it narrower and narrower, just short of the short circuit. I don't want to have it short circuit. But I make it narrower and narrower, actually wave tunnels through this better. At first, we didn't believe this. We tested. We examined. Everything was consistent. Maxwell's equation satisfied everything. Then we decided to do the simulation. Everything worked out. Then we decided to do experiment. Everything worked out. And indeed, actually, this became an interesting area in metamaterial, that this ENZ structure can give us very interesting, unique tunneling that is very different than Fabry-Perot tunneling. That's very different. It's specifically for this ENZ. Now, let me show you a simulation just to get a feel for it. Imagine I have this. Oh, by the way, one thing I forgot to mention. This formula doesn't say anything about this angle. In other words, you can make this waveguide bend 180 degrees and still no reflection will go through. So in other words, it makes the waveguide looks like wire. In our room, if I get that wire and bend it, it's not going to stop the current. But in electromagnetic waveguide, if I bend the waveguide, it's going to have reflection, but not here. If you fill that region with ENZ structure, you can bend the waveguide without any reflection. So let's take a look at it. If I take a look at this structure, perfect conductor wave is coming like this, what do you expect to happen? If I just come over here, it's going to reflect all of it. Here, look at that. I send this wave. No material over here, it's just air over here, and then of course everything reflects back. That's not surprising. But now what I'm going to do, I'm going to fill this region with the material, and I'm going to make the permittivity of that material start from 1, and I'm going to come to lower value. Let's see what happens. If I started at 0.5, you notice, of course, most of it is still reflected, but there's a little bit of this, leaking out over here. Let's make epsilon 0.1. You see, good amount is going through. Let's make epsilon 0.001. All of it will go through. All of it will go through and squeeze through this very narrow channel and goes over here without any reflection. It's coming over here. So this phenomenon, we call it ENZ supercoupling. And actually created quite an interesting phenomenon after that. So we looked at this in an optical system. We look at this in Purcell effect and so on. I don't want to bore you with all those details there. Let me just concentrate on just a few, and then we finish the talk. So you might say, OK, this is fine, but do we have a material with ENZ structures? The answer is yes. In fact, there are several classes of material that could do that. For example, in the near IR, transparent conducting oxide, indium tin oxide, aluminum doped zinc oxide, gallium doped zinc oxide, they have a 0 crossing at about 1 or to 1.2 micron. That's close to telecommunication wavelength that we have there. This is a result, by the way, this experimental result obtained by my collaborator, Sasha Boltuseva from Purdue, that we actually have a paper together in this regard. And indeed, you see that these are the 0 crossing of this. Now, these materials, by the way, the imaginary part of permittivity is not too small. So the range of the application of this material is limited. However, if you go to mid-IR, silicon carbide, excellent, by the way, in this aspect. Silicon carbide has a zero crossing of permittivity at 10.3 micron. And that's very close to CO2 rates that we have there. And so we have it also in topological insulator that Nikola Tesla found. You can do it, actually, you can put together material, and you can design a metamaterial that would give you the epsilon near zero at the wavelength you want. You can do it with the photonic bandgap structures that you can have a Dirac dispersion with accidental degeneracy. You can do it in a waveguide, just empty waveguide. Just empty waveguide. If you operate it with TE10 mode near a cutoff, you can actually have E and Z property. In fact, that's how we did the experiment. So what we did the experiment, by the way, with the waveguide at cutoff, and indeed we showed that even though you change this weight over here, you actually have the transition through this as going through. Now, in the interest of time, let me just jump over some of these properties of the photonic doping, and then we can stop. So one of the interesting points about this is that if I start with a structure like this, and the magnetic field around here is completely uniform in this structure. So if I go to this structure, which I call it photonic doping, and I put one dielectric rod over here, you can show that even though you add this dielectric rod over here, the effective permittivity from outside does not change, but instead, the effective mu does change. Now, this is interesting. In other words, none of these materials are magnetic. And yet, you combine them in a very interesting way, and to the outside observer, looks like different mu that you have. So you can have mu very high. You can have mu very close to zero. So for example, in this case, we designed this structure such that effective mu is also near zero. So as a result, you can think about this blob of structure over here whose epsilon and mu is near zero. That means the wavelength becomes infinitely large. That means even though you have a structure that is physically any size you want, but electromagnetically is 1 point. Which means if you put two quantum emitters here and there, the quantum emitters interact and entangle with each other just like they're in the near field of each other, even though they're far apart. Because that region actually behaves as a point. So, and this, you can actually have a magnetic mirror as well to do that. Now, let me jump over, I know there's no time, but let me jump, oops. One of the interesting features is that we found out that there is an interesting analogy between Meissner effect in superconductivity and this structure for epsilon near zero. Now, you all know that Meissner effect would cause the magnet to suspend or levitate over a perfect conductor. And the reason for that is the magnetic induction B cannot go into the superconductor. Now, for the case of E and Z, it's the dual of that, but from classical point of view. So vector D has to be equal to 0. So you put an electric dipole on top of this, the electric dipole should be levitated. So we theoretically proved this, by the way, in this paper, and we showed that indeed, there's a very interesting range of permittivity of the substrate that if you have an electric dipole on top of this electric dipole could be levitated. Now, this is a theory so far, but we are working with my friend, Pino Strangi in Case Western Reserve University to actually try to show this experimentally. If we can show that we can actually levitate the particle by just shining the laser light over here, you can levitate and you can actually completely remove the friction. And you can have a microfluidic system to walk over there, kind of like the nano system of the magnetic levitation. But this would not be magnetic levitation, it's actually electric levitation to that. Anyway, and the cavity I promised to show you is that you can actually have a cavity structures like this with the arbitrary cross-section, arbitrary shape, such that you can have a very interesting mode inside of this. This mode is electromagnetic mode that you have, that inside this dielectric you have magnetic and electric field, but in the E and Z region you only have electric field, but no magnetic field. This is the decoupling I mentioned to you, that you can decouple E and H. This structure can actually hold electromagnetic energy even though the boundary of that is open. And the reason for that is the electric field comes over here and has only normal component. But when you sit outside the structure, the electric and magnetic field is 0. And the reason you can do that is because epsilon is 0. So vector D is continuous. Anyway, so, and you can have different cavity shapes, very different cavity shapes, but all of them with the same resonant frequency. So let me finish up by just finishing. Oh, by the way, let me actually show you the experiments too. Indeed, we actually did this experiment in the microwave region. So what we did, we built 3 different cavities. Intentionally very different shape, intentionally. You notice the external shape of this is very different, but the cross-sectional areas are the same. I didn't get a chance to go through the detail of the formula I showed you, but that formula that I showed you for effective mu, it only depends on the cross-sectional area, not on the shape. So if I kept the cross-sectional areas of the cavity the same, and I put a dielectric rod here, what we want to test is to show that all these 3 cavities would have the same resonant frequency. That's number 1. Number 2, the location of this rod doesn't matter. I can put it anywhere I want. So you see the 3 spot. Actually, that doesn't mean that there are 3 dielectric rods. It's only 1. But we repeat the experiment on different points. So we have 9 different experiments over here. We did that. We built the structure in microwave system. The structure is like this. And we put them together. And we did the test. And look at it. All the resonance system coincides together. Even though the 3 cavities are completely different shapes, and the location of the rod is completely different location, in all these 9 scenarios, the resonance happened over here. And let me just finish by saying the following. Through this development of this ENZ photonic doping, we came across accidentally. We came across an interesting analogy with the transformer. Now, if you look at this structure over here, so this structure consists of ENZ region and dielectric rod, is a periodic. You can design this thing such that this will look like a magnetic mirror, which means the effective permeability would be very high. Even though none of these materials are magnetic, but using this photonic doping, you can actually create the scattering system that when the wave comes over here and reflects back, it looks like a magnetic wall. Okay, that's fine. That means the magnetic field is very weak, and magnetic field concentrate on this rod over here. So take a look at it. Over here, magnetic field is 0 on this boundary, so you have a complete standing wave over here. Magnetic field here is very close to 0 and is concentrated on this rod, and this is electric field distribution. But one of the things we noticed, by the way, accidentally, that this electric field distribution is very, very high around here. Now, usually we have high electric field in plasmonic system. Those of you who are familiar with plasmonic system. But there's nothing plasmonic about this. In other words, here, epsilon is 0 and epsilon is positive. I don't have any epsilon negative anywhere that to have plasmonic system. So this is another way that you can have a very high electric field over here. But then we said, this reminds me of something. So then 2 of my scientific heroes, one is Nikola Tesla, the other one Richard Feynman. Nikola Tesla, you're all familiar, by the way, did, of course, the transformer, Tesla coil, and all of the things, the fathers of electrical engineering. But Feynman was the one that actually also predicted the nanoscience, back in 1959 in his famous, speech of there's plenty of room in the bottom. So I said to myself, is it possible that we combine these 2 guys together in the nanophotonics, and actually that comes into this photonic doping? Let me show you why. If you look at the structure I showed you over here, and I send a wave over here like this that I showed you before, what I'd like to do is do the following. I come over here, and I actually find the line integral of electric field around here. Okay? If I do the line integral of electric field according to Faraday's law, that should become the total flux that I have over here, the time derivative. But the beauty of that is inside of this magnetic field is 0 here, but magnetic field is concentrated in this rod. So if I want to find the flux, the only thing I need to do is to go on this rod and look at the flux of the magnetic field there. Okay? So obviously that should become equal to this, time derivative of that, of course. But then what would happen if I come around this region? So if I come around this region and find the electric field integrated around here, I would get this. Now, according to Faraday's law, this line integral, which is equal to time derivative of the flux here, and this line integral over here, which is equal to time integral of flux here, should be the same. Because I don't have any magnetic field over here. All the flux is concentrated on that rod. So it means these two guys should be the same. Which means that I can actually have a very interesting relation between the intensity of electric field here and intensity of the electric field there. Now, what does that remind us of? That reminds us of the transformer. If I have a transformer, I have a primary and secondary, the ratio of voltage 2 over voltage 1 is N2 over N1, number of turns. Why? Because the flux is the same. It's going through both of them. Now, in nanophotonics, I don't have turns, but instead, I have a perimeter. So I can actually change the perimeter of the system and have the effective transformer in the nanoscale. So this one, you notice that if I can change L compared to this, I can increase B. So effectively, this is like, the nanoscale version of the Tesla coil, but in the nanophotonics. So essentially, you can actually change this length, and you have different intensity of the electric field. So very interesting way you can actually transfer the intensity of the electric field from input to the output, just like the primary and secondary that you have. So let me stop over here. First of all, I want to thank again, the department and my friend Victor and all the colleagues and friends for giving me a chance to be here. So I wanted to share with you, by the way, some of this extreme sense of photonics over here. Of course, there's no time to go through all of them, but I just wanted to share with you two of them aspects. One, the structure that can actually do analog computing for you for the materials. So in other words, I like to say, let the materials do the math, and this one can do. And another thing is that how to actually use the concept of photonic doping using the epsilon near zero material that will give us quite a series of interesting phenomena, some of which I describe over here. For those of you who are interested, by the way, we had two review articles that recently came out. One of them is the extensive review that we had in Nature Photonics that came almost a year ago. And the other one is a shorter one that we had earlier than that. And some of the aspects of quantum photonics and quantum optics that you can find in this. With that, I thank you very much for your attention. Thank you.
Any questions for Professor Engheta?
Yuri.
So for your analog computing approach,
sure.
If I'm trying now to understand where the program is, you're programming the epsilon and mu, that's your program.
That's right.
So in some sense, in order to have it programmable, you need to change epsilon mu on the fly.
That's right. And
otherwise, it's just a static filter with restricted interference.
Exactly right. And to answer that question, we have another technique that I didn't get a chance to talk about. And that is the collection of Mach-Zehnder interferometers. In other words, you can actually do the same scattering problem by collection of Mach-Zehnder interferometers with different phases. So there, we can easily change the phase of the Mach-Zehnder, and we'll change the scattering, and we'll change the kernel, very similar to the permittivity being function of x and y. So yes, you need to change the kernel if you like to change the kernel completely. But for each kernel, you can do it with arbitrary input. There was no time to go to the other technique over here. But one of the things I mentioned, there are two approaches we have taken in making the kernel there. One is the material approach, which is epsilon as a function of x and y, which, by the way, even that, you can actually change it by phase change material. I mean, you can do that, just like a CD-ROM, that we can change that. That would be similar to that. But better than that is the other approach that we are doing with the MZI, or Mach-Zehnder interferometer. So Mach-Zehnder interferometer is essentially a collection of several of them, 30 of them, let's say. Actually, that one we also started an experiment, and I'd be happy to show you some slides. So there you have this 35 Mach-Zehnder interferometer, each of which you have 2 degrees of freedom that you can change the phase. So for every kernel, you can go and change those 70 phases, and you can have completely new kernel. And you can do that. So that you can change on the fly. Sure.
In some sense, you need to calculate your result first. Then put it in the structure, and then it will just prove that your calculations are correct, or will go to some, something that is close to what you calculated already. So it's not really a processor.
Excellent.
If you calculate it first, it solves the problem.
Sure.
to make it work in optics.
Excellent, excellent point. That's, again, one of the reasons, by the way, that first of all, actually, if you give me the kernel, then I have to do optimization to find epsilon. However, when you have the epsilon, then you can have any input you want. Remember, I is completely arbitrary. I is completely arbitrary. Then you can actually use any input you want and you get output of that. That's one thing. But even to address that question, that's a very important point you're raising. That's one of the reasons. In the case of MZI, there's actually a very simple algorithm that if you give me the kernel, I can go ahead based on the algorithm, find out what are the phases. I mean, that's pretty straightforward. The price you pay, by the way, for MZI is a longer system. I mean, the material is much more compact, but yes. So, but when you have the kernel, whether it's changeable, reconfigurable, or not, please remember that the input is arbitrary. Then you can have for any input.
I have a quick question.
Sure.
You mentioned about the three basic elements
Yeah.
in circuits, resistors, capacitors, and inductors. And you touched upon the doping too,
Yeah.
right? Photonic doping. So one of the key elements in circuits is transistor. Right? And you're sort of moving in the direction that you're starting to having doping materials. Do you envision having a transistor which will give you even more programmable type of computation?
Certainly, one of the reasons, yeah, I mean, let me answer it in this way. When we actually introduced the circuit elements, naturally, I mean, the next question was a transistor. However, as one of the interesting features in electronics is that if you give me a transistor in electronic, you can have three different functionalities coming from that depending on how you bias it. You can make it as a switch. You can make it as an oscillator if it's unstable, I mean, branch of that. Or you can make it, as amplifier. At first, we tried to see whether we can find one single optical nanostructure that would do all those three functions. We could not find that. So we decided to actually divide our goal into three. So in other words, can I have one nanostructure element that would do one of those three functions? Let's say amplification. That we have come up with a design. Actually, I can send you the paper. That if you combine the non-reciprocity with the gain material, you can actually have equivalent of metatronic transistor for amplifications. That we do. Now, the switching also we have done with the phase change material. The things that are left to be done is that can I have an optical element that when I bias it somehow, it will give me actually the oscillators. That, we haven't done that yet, and I believe this photonic doping may be the step towards that.
One more last question.
Yeah, I have a short question.
Nice to see you.
Yeah. You mentioned that in the medium with, zero epsilon and mu, right? E and H become decoupled at steady state, right?
Yeah.
The question is, when I turn on signal, transient signal, how much time would it take to reach steady state?
Excellent
Were it
question.
ever established?
Yes, excellent question. Actually, I have slides for that as well, but not in this talk. Yes, what happens is that, yes, obviously in the steady state, it takes some time. Just to give an idea, by the way, how long does it take, it's actually pretty straightforward, I mean, back of the envelope calculation. Look at the size of your structures and look at the Q of your system. From that, you can find out what is the group velocity that you have. Divide that size by that group velocity. That will give you the time scale that would take to come to the steady state. So if your system is very large, let's say, I mean, several wavelengths, then your Q is high for this system. Then group velocity is lower. Then it takes a longer time for the steady state to come. But regardless of that, actually, one of the calculations that we have done is the group velocity is not that bad. It's about C/10. So that's still pretty fast. I mean, if you look at velocity of light and C/10, that's actually quite fast. But yes, but that's the back of the envelope calculation that you can do to get that. Size divided by group velocity. Ken.
Awesome.
So one of the challenges is to convert very detailed permittivity profiles, to advice.
Sure.
And that's always there's always that challenge. So my question is very simple. Is there an example where extreme photonics has been applied, that we can, an everyday application that would be
Sure. I mean, the good example of that is graphene. Graphene. I didn't talk about that over here. Well, I mean, not yet in the everyday devices, but people have shown, by the way, a lot of interesting modulator, for example, come from here. Very high nonlinearity, come there. For example, we propose the ideas to start with the graphene as a one-atomic optical devices, and later on, Dmitry Basov actually showed that indeed that's possible.
The motivation behind my question is that when I was a grad student, optical computing was the hot buzzword.
Yeah.
And it died.
It died. You know why it died?
And indeed, because it was just way too big, too bulky. And silicon raced on ahead.
That's right.
And similar to Yuri's comment, if you have to do a lot of calculations to get the answer to make the thing, and then
Sure.
we're always behind. So
That's
I'm
right.
worried that I don't want to hear computing.
No. And you notice, by the way, I didn't say optical computing.
I know that.
And because the optical compute, the reason, by the way, that died, because they wanted to do it in digital system and optical logic. This is not optical logic. No. This is analog computations, pure and simple. I'd never claim that this would be an optical logic. Yes, in that case, electronics is far better than that. No question about it. And the reason for that is because nonlinearity in electronics is much better. I mean, it's much cheaper, nonlinearity. But nonlinearity in optics is very hard to get, as we all know. Now, so definitely this is not optical computing. This is just optical structure try to do analog computing. That's very different. So there is no optical logic. There is no optical binary system or anything, not at all. And I want to make this very clear. Coming back to Yuri's question, and Yuri's question is very, very interesting. Yes, you need to have a system that you can implement the kernel much faster. And that's exactly one of the reasons, by the way, we are also studying the second approach to that in Mach-Zehnder. Mach-Zehnder controlling the phase is very, very rapid. You can do that. And that's also analog system. There's nothing digital there at all. But having said that, even when you have a kernel ready, then any input, you can get the output very quickly. So this is important. I emphasize this. It's not just implementation of the kernel. It's also variation of the input. So let's say, for example, I'd like to find out what is the temperature distribution in this hall. And in order to do that, I have to, if for any given source that I have over there, there's an integral equation for that to find. So if we know that integral equation, that kernel is known. If we use this one, then you can give me any heater that you put inside this room, I can immediately tell you the answer. It's the same kernel. I don't need to change the kernel by putting the heater here or there or there. It's the same kernel. If you want to change the problem from, let's say, thermodynamic, let's say, I don't know, to, nonlinear dynamics, then that's a different kernel. Then we have to go and build a different kernel, and even that can be done with MZI.
All right, let's thank Professor Engheta one more time.
Thank you. Thank you very much.